Okay, so we will start. Welcome everyone to this one-word seminar on machine learning. Today, our speaker is Yaoyu Zhang. Yaoyu is a tenure-track associate professor at the Institute of Natural Sciences and the School of Mathematical Sciences, Shanghai Jiao Tong University. He earned his bachelor degree in physics from Zhang College from Shanghai Jiao Tong University in 2012, and his PhD in mathematics in 2016. And from 2016 to 2020, he conducted his postdoctoral research at NYU Abu Dhabi and Grant, as well as an Institute of Advanced Study in Princeton. His research focused on theoretical foundations of deep learning, with his work published in prominent journals and conferences. So today we will welcome Professor Yaoyu to give a talk on optimistic estimation. So please share the screen, Yaoyu.
Okay, so can you see the screen?
We need to wait a bit. Oh, okay, now we can see the screen. You should the full screen.
Okay, is it full screen?
Yeah, it's okay now. Now you can start.
Okay. So thank you, Zhiqing, for the kind invitation. And today I'm going to talk about the optimistic sample size estimate to understand the deep neural networks. So I think probably the biggest news in these days is the 2024 Nobel Prize in Physics was awarded to John Hopfield and Hinton for fundamental discoveries and inventions that enable machine learning with artificial neural networks. So it is some kind of surprise, but if you look at what they are doing, they emphasize the importance of the similarities of the artificial neurons with the spin models in statistical physics. So this kind of similarity that lead to their research or their inventions of the Boltzmann machine as well as the Hopfield network. Therefore, this year's Nobel Prize in Physics recognized the research exploiting this connection, means a connection between the artificial neurons and the spin models in statistical physics to make the breakthrough. So I would like to say that in my personal view, this is the success of theory-inspired models in AI. However, as you all know, that we have very, very limited success of theory-inspired models in today's development of deep learning. So let's ask the following question: what theory may inspire the next generation model? Of course, many people may be pessimistic about this. Okay, they may say maybe next generation model we can make the next generation model without any theory. But is it possible that we may have a theory that could really help us? If so, this next generation model can really build up on a solid foundation so that the development of this model, we can really be more confident about that, and those understanding could really help us with the future development of AI. So we see that the spin theory from the statistical physics inspires this Hopfield network and the Boltzmann machine. But so is there any existing theory, for example, from other areas that could inspire the next generation? Actually, I'm pessimistic about that. There's already exists some theory that in some in some disciplines where we really knows in our community. I don't believe in this because I think in these 30 years of development of AI, people from all different disciplines have tried to apply their insights to build up some AI models. But what we see now is just what you see, like CNNs from the neuroscience or like the ResNet or transformer. I would rather say they are a success of engineering efforts. So then that leads to the fact that probably we don't have any theory in hand now that if we just find it somewhere, then it directly inspires something new. Probably we need to build up for the current AI ANs first. So it does not exist, but we need to build up this theoretical understanding. So probably if we have deeper understanding of the current neural networks, this can give us some better inspiration of what next generation model could look like. So today, I'm going to focus on a very specific direction of this current understanding of deep neural networks. Essentially, I'm focusing on the estimation of the sample efficiency. As you all know, that when we talk about neural networks, we may say, okay, training, generalization, and so on. But now, with the development of large language models, it turns out that the sample efficiency, this kind of quantity are really important, because as we can see that we have due to the scaling law from the OpenAI, the test loss can always drop if we scale up the data set size as well as something else like the model size. So it's really a resource issue for the models to achieve certain kind of test loss. But now the most important thing for the model is the sample efficiency, meaning that if we fix some kind of test loss or fix some kind of performance requirement, I can ask how many data it requires. If a model requires less data for a high performance, then this model really shows out to be the more powerful one. And we can expect that the next generation model may require less data for a higher performance. So if we can really have some models with higher sample efficiency, and then I think this kind of model could really help or can have some promise to be the next generation. Therefore, theoretically, estimating the sample efficiency becomes a very important problem. So there's one keyword in my title, that is optimistic. So we can think of any kind of estimation of the sample efficiency, but we want to emphasize optimistic perspective. But why is that? So let's first talk about some pessimistic kind of estimate based on the worst case understanding. So let's think about a very simple target. This is a first order polynomial. We can use the polynomial of higher orders to fit this simple target. So we can use a polynomial of, for example, 100 degrees to fit this simple target, then the sample size scale with the parameter size of the model. With this kind of solid understanding, we can see that the parameters should not be multiplied unnecessarily. Otherwise, we can see that to achieve the fitting or recovery of the target, we require tons of samples. That means a reduced sample efficiency. Let's think about the neural networks. So for the previous linear models, our understanding is we should not increase the parameter size unnecessarily. But for the neural networks, it seems that we can always increase the number of parameters to improve the performance. So this is the experiment from OpenAI. We can see that as these dots goes lighter, the parameter size becomes larger. And we can see that there, for the tokens from 10 to the 7th to the 10 to the 10th, in this whole range, the largest model consistently performs to the state of the art. Therefore, we do not really need to think about the data set we have. We blindly choose a larger one so that it brings us some good performance. So that tells us that increasing the parameters could benefit the sample efficiency. So this is totally different from the previous understanding that the sample efficiency decreases with the increase of samples, with the increase of parameter size. Okay, so as we all know that in deep learning theory, there are many long-standing problems. Some of these problems can be translated into problems regarding to the sample efficiency. For example, the first problem proposed by Liu Breeman, why don't heavily parameterized neural networks overfit the data? So this question can be translated into why don't over-parameterized neural networks reduce sample efficiency? And the second question is, what is the effective number of parameters? This problem can be translated into what is the sample size required for fitting. As we all know that, so they propose this question of effective number of parameters because they think, okay, since we don't need so many samples, maybe your effective number of parameters is low. So based on understanding that the sample size required for fitting is actually a way to quantify the effective number of parameters. So we have this, if we solve this problem of the sample efficiency or sample size requirement, actually this gives us a way to quantify the number of effective parameters. Okay, so now based on these questions, my talk will give you some answer about these two problems. And now let's go to the optimistic estimate. The basic idea of optimistic estimate is, at the best possible scenario, what is the sample size required for fitting? So our motivation of addressing the sample size estimation problem is that we observe as we increase the parameter size of neural networks, the sample efficiency may not reduce in practice. So before we dive into this problem, we need to tell you that there are two ways to increase the parameter size of the neural network. One way is to increase the connection. For example, this original neural network has only local connection. But if we connect all these previously unconnected weights, then we obtain more parameters. And another way is to increase the width so that the neurons in this layer increases. That also leads us to a neural network with 24 parameters. So we must distinguish these two different cases in order to understand the effect of parameter increase for the sample efficiency. For the estimation of sample efficiency, we must have a really clean setup. So in this setup, we consider a target function that is generated from this simple neural network with 12 parameters. And we consider to fit or recover this target with 3 different neural networks. The first one is as small as the target. And the B and C has more parameters. And we want to see whether increase the parameters harm the sample efficiency of recovering this target. If we borrow the insight from the classical estimate, which tells you that as long as you have more parameters, you must increase the sample size. Therefore, by the classical estimate, this is kind of worst case estimate. For the neural network A, it requires 12 samples, and for B and C, 24 samples are necessary. And if you believe that the worst case estimation reflect the reality, then the conclusion is if we increase the parameters unnecessarily, then the sample efficiency should reduce. Of course, it does not reflect the reality of the neural network. And actually, with a new sample size estimate from the optimistic perspective, we will give you a different estimate that tells you that with a neural network C, meaning that if we increase the number of neurons, the number of samples required for fitting is still 12. With this new estimate, you can see that increasing the number of neurons will not reduce sample efficiency. But how to do that? That leads us to a very important phenomenon we call condensation. The condensation basically is a well-observed phenomenon during the nonlinear training of neural networks. Basically, it tells you that the neurons has kind of clustering behavior. For example, if we randomly initialize the neural networks, all these weights of these different neurons are different. However, after training, this could happen that the W1, meaning the these neurons' input weights become exactly the same as the input weight of the second neuron, which means W1 equals to W2. And also the third neuron, fourth and fifth, their input weights could be exactly the same. That is the meaning of the clustered, or we use the word condense. When the neurons condense with one another, we can see that these neurons can be combined into fewer neurons. For example, 1 and 2 combines into one neuron, and 3, 4, 5, these 3 neurons combines into another neuron, which leads to an effectively smaller network. This smaller network, this network equivalent to a smaller network means that at this state, the neural networks has fewer degrees of freedom. The fewer degrees of freedom meaning that if you have only limited sample size, this limited sample can better constrain these limited degrees of freedom. So that is the intuition of condensation improves sample efficiency. So we previously have serious works on the phenomenon of condensation. This phenomenon is not easy to study because it's highly nonlinear. So, but we make some progress about the condition of the condensation, meaning that in, for example, a two-layer neural network at the infinite width limit, there's a linear regime, meaning that it's similar to kind of neural tangent kernel behavior. And there's also this regime called condenser regime, where neurons behave extremely nonlinear, and the neurons tend to cluster with one another. And we also have analysis about the initial condensation, meaning that at the initial stage, the neurons will become very similar to one another. So, but later, these neurons can split if the data is complex. Of course, we also have some studies about the condensed critical points, and we can prove that in the landscape of the neural network, there are lots of condensed critical points. And also the final stage, the global minima geometry also informs us about the condensation at the final stage. So with the phenomenon of condensation, we can have a better estimation of the sample efficiency. For example, if we still consider this target generated from this smaller network, when we have a neural network with more neurons, we first think about a condensed state that can express the target, but at the same time is sufficiently condensed so that it is equivalent to a smaller neural network. And using this equivalence, we can just use a classical estimate that tells you that the number of samples required equals to the number of degrees of freedom or number of parameters. And now for this smaller network, the number of parameters of degrees of freedom is 12. So this gives us the optimistic estimate of the neural network C in fitting the target at start. So, and now we go to the mathematical definition of the optimistic sample size. So a very important quantity for the formal mathematical definition is the model rank. The model rank is a quantity that can quantify the extent of condensation. Let's first look at these forms of the definition. We can treat a model or a parameterized model as a mapping from the parameter space. For example, the neural network may have a capital M number of parameters. So given a parameter vector, it gives you a function, for example, in a subset of the continuous functions. And for this kind of mapping, for many neural networks, we can see that it's differentiable. Therefore, we can take the derivative and also compute the rank of its derivative. And a more straightforward definition is this following one. So what we do to compute the model rank is we take the partial derivative of this mapping F for each parameter. So since there are capital M number of parameters, so here we obtain capital M, we call tangent functions. And we can span all these tangent functions and compute the dimension. These essentially ask how many linearly independent tangent functions are there for around this theta. So this model rank essentially captures the effective degrees of freedom at theta, but in the function space. And essentially, we can see that if we have a system with stronger condensation, we can expect a lower model rank at the condensed parameter state. And a lower model rank can also give rise to a higher sample efficiency because the lower model rank indicate a lower degrees of freedom locally. Let's look at the relation between the condensation and model rank from the following simple example. So this is a two-neuron neural network with 4 parameters. And the model rank can be computed as follows. We first compute the tangent functions. Essentially, we take the partial derivatives with respect to A1, W1, A2, and W2 respectively. And we obtain 4 tangent functions. And we can span them and compute the dimension. And we can see when the network is in a condensed state. For example, the W1 equals to plus minus W2 because it's tanh, because of the property of this tanh function. And at this condensed state, we can see that these former 2 tangent functions are linearly dependent or linear correlated with these later 2 tangent functions. Therefore, the dimension or the model rank is less or equal to 2. But if the network is not condensed at all, meaning that the W1 does not equal to plus minus W2 and is away from 0, as well as A1 and A2, and the rank is consistently 4. So from this simple example, you can have some understanding that the condensation means a lower model rank. Therefore, we can use this model rank to formulate, define these sample size estimation we previously obtained via the intuition of condensation. And now let's go to the basic setup. So these are all very standard setup of the current deep learning. So we have some data set, we have n samples, and we have a model which gives you a mapping from the parameter space to the function space. And the optimization, we have some, for example, the MSE loss and some gradient descent optimization. And we want to ask how many samples are required for fitting certain f star. And one remark I have here is, if this f is a linear function, then you can solve this problem exactly. However, if I turn this f to a nonlinear function or a nonlinear mapping, for example, a neural network, then all the understandings about this problem are missing. And now let's see how we do to get an optimistic sample estimate. So this is just the previously defined model rank. To obtain an optimistic sample size required for fitting an f star, which can be expressed by the model, we first look at this set, which we call a target set. Essentially, this target set gives you all the theta that can exactly recover the f star. From all this set of theta, we obtain the minimum value of this R theta, essentially the minimum model rank among this target set. And this gives you the optimistic sample size. Essentially, we are finding the most condensed theta that can express f star and use these effective degrees of freedom around these most condensed theta to be the optimistic sample size. So the intuitive procedure is as follows. We have a target f star, and then we find a theta star in the target set with a minimum model rank. And then this minimum model rank is given to the optimistic sample size of this target. Okay, with this formal definition of the optimistic sample size, we can actually estimate this for a variety of nonlinear models, including the deep neural networks. But this number has some properties that we need to keep in mind. First property is that it's optimistic, meaning that it is kind of a lower bound of sample size for fitting. And it is not necessarily the practical sample size for the recovery. And second is a target adaptive. So if we have a simpler target, then we require less, it will give you less samples, because as we can see that this target function is very important for the optimistic sample size. And in general, for the general nonlinear models, this optimistic sample size changes for the different targets in the function space of the model. And the third is tuned for realization. The realization of the optimistic sample size requires strong condensation. And this requires some conditions for the realization. And the general picture is that for any model, given a target it can express, we can have a pessimistic estimate, means just use the parameter size. And of course, we can also use a previous definition to get an optimistic sample size estimation. This gives you kind of lower bound for the sample size. And in practice, you could, in practice, the sample size required usually is somewhere between these two numbers. But is it closer to the optimistic one, or it is more likely close to the pessimistic one? Let's see from the following experiments. So first of all, we have some theoretical result regarding the optimistic sample size for two-layer neural networks. So essentially, the understanding is that if the target function can be expressed by k neurons, and you are using a M neural network, this M neuron can be extremely large. For example, this M can be 1 million, and this K can be 3. And this optimistic sample size tells you that this optimistic sample size only depends on the intrinsic complexity of the target, meaning this only K times the D plus 1. It is independent to the number of neurons of the neural network. Okay. And if we just use a pessimistic way to estimate, use the classical estimate, then you can see that the sample efficiency will decrease with the increase of the neurons. However, if we believe the optimistic sample size reflects reality more or better, then the optimistic tells you that the efficiency preserves, meaning that as you increase the number of neurons of the neural network, the sample efficiency preserves. And this is our experiment. We use the same target function, but using neural networks with different widths. And this 100 times, meaning the width or the number of neurons in this neural network is 100 times this neural network. And the optimistic estimate tells us that this optimistic sample size is the same. Theoretically, for this problem, it is 21. And we can plot the actual training of the neural network, the test error in this color, and the red means 10 to the minus 6. It's a very, very low test accuracy, meaning that the neural network almost recovers the target function. And we can see that the yellow curve is very close to these transitions when the neural networks turns red, deep red. And let's look at a specific experiment here. And in this experiment, this is 3 times the neuron of the minimum network that can express a target. The optimistic estimate tells you that the optimistic sample size is 21, and the pessimistic estimate is 63, because this model now has 63 parameters. The practical, with good tuning, the practical sample size required is about here. You can see that it's close to 21 rather than 63. Let's look at a more extreme case. And for this case, we consider a network 100 times with 100 times more neurons than necessary. And the optimistic one is still 21. And now the pessimistic one becomes over 2,000. And we can see that with good tuning, the practical sample size for target recovery is about here. So here it's about 30. So it's still very, very close to the optimistic one, and it's far away from the pessimistic estimate. And now you may have some confidence on the optimistic estimate that in many situations, our optimistic estimate reflect the actual performance of the deep neural networks. And now let's look at how different, for example, the parameter size affect this optimistic sample size. The first theoretical result is wider network is sample efficient by this inequality that the optimistic sample size of the wider network is always less or equal to the optimistic sample size of the narrower network. And if both of the network can express the target. And also with this corollary, it says that increasing the width will preserve the sample efficiency. This can be an explanation of why in practice we are expecting that when we increase the width, the performance will not drop. And we can also try to understand via the optimistic estimate the impact of the connections to the sample efficiency. What we compare is, for example, we can compare the sample efficiency or sample size requirement for a CNN and also a CNN with no weight sharing. And we have these kind of theoretical results, but let's just look at this table, which summarize these theoretical results. It tells you that if we first have a CNN with no sharing, but only no local connection, and then we can increase the complexity or increase the number of parameters so that all these connections are added to obtain a fully connected neural network. If for both of these neural networks, we ask what their sample size requirement for a CNN function with k kernels, and these are the results we need to compare. And these K, S, D are the, for example, the convolution kernel size and the input size. So let's look at the following example. So if we have some MNIST data, for which the input size is 28 by 28, if the target is with K, meaning that we have a K kernel convolution network as a target, the kernel size is 3 by 3. And if we use a CNN, a YCNN to fit the target, it requires 685K samples. And without the sharing, we need 10 times more samples. And if we add all these connections, and it requires additional 100 times samples. So meaning that in this very specific case, if the target can be expressed by the K-kernel CNN, then using CNN is 1,000 times more sample efficient than the fully connected neural networks. That tells us why we never use fully connected networks for the image problems. We can also perform this numerical experiment to verify our predictions. Our prediction is that if we have a target that can be expressed by CNN with sharing, our optimistic sample size is relatively low, indicated by this yellow line. And if we estimate the optimistic sample size in CNN without sharing and the fully connected one, the optimistic sample size becomes larger. And in practice, we can verify this, the transition of the performance that tells the practical sample size for fitting also becomes larger for the fully connected one than the CNNs. You can see a close match between the optimistic estimate and the practical transition. So this tells us the added connection reduces the sample efficiency. Okay, now let's go to a very important question is, what is special about the deep neural networks in terms of the sample efficiency? And in the conventional model and also our estimates, we should never add unnecessary parameters. But for the neural network, adding unnecessary connections is problematic. It's not sample efficient. But if we add neurons, this is optimistically is very sample efficient, meaning that the sample efficiency does not reduce as we increase the width of the network. So this red one is some property we never see from a conventional model. But for the neural networks, this property, you can see that the layer structure is the key of the neural network architecture. And for all the neural network, whatever the variations, and you all have this width dimension. And if you increase the width, you don't need to worry about the deterioration of the sample efficiency. And this gives us the two principles for the model scaling. The first is we can freely increase the width, but we need to refrain from adding connections. And there's a very interesting analogy with the evolution of our brain, as we can see that from the mouse to human, the number of neurons increase by 3 decades, meaning 1,000 times, but the connections per neuron are kept at the same level. So by the evolution, it seems that our cortex prefers to increase neurons rather than the connections. So this also, it's a very similar to these inspirations from our analysis of optimistic estimate. Okay, so as I tell you some properties of the optimistic estimate, but estimating the optimistic sample size for a model in general is complicated, but there's some shortcuts, meaning that if we observe some permutation symmetry, this permutation symmetry automatically guarantees the sample efficiency preserving as this dimension increases. For example, we can see that all the neural networks, if you change the index of 2 neurons within the same layer, the neural networks, the function are exactly the same. That is called the permutation symmetry of the neural network model. And the permutation symmetry will give rise to an invariant manifold of the gradient flow. Essentially, if we find some permutation invariant manifolds, for example, if the J's neuron and the J prime's neuron, their weights are exactly the same, they during all the training, the whole training process, they will remain the same. So this gives you a lot of invariant manifolds of the gradient flow. And these invariant manifolds, on these manifolds, it is equivalent to a smaller network. And with some more sophisticated theoretical analysis regarding the optimistic estimate, and we can obtain that optimistically, the large networks or wider networks are as efficient as smaller networks. So observing the permutation symmetry gives us a shortcut to understand the impact of certain widths to the sample efficiency. And now we can apply this, for example, to this transformer. And we can see that in the transformer, the embedding dimension, attention dimension, and the number of heads, the heads dimension, these 3 different dimensions all have the permutation symmetry. And therefore, we can conclude that optimistically, we can scale up all these 3 dimensions freely. As you can see from the practice of the scaling law experiment, they really scale up the model via these dimensions rather than some dimensions that is related to the connection. And probably lots of you know a new architecture called CAN. This is inspired by the Kolmogorov-Arnold representation theory. So it is nevertheless a nonlinear model that we can perform optimistic estimate. So we can observe that this index of I is similar to the width of the neural network, has a permutation symmetry. And with the previous result, we can conclude that increased M preserves the optimistic sample efficiency. However, if we observe this dimension Ci, which is the coefficient between these basis functions, these coefficients has no symmetry. And Therefore, we can conclude that increase G, the number of grids, reduce the sample efficiency. And we do the experiments. So the x-axis, we plot the parameter size, but for the blue curve, we increase the parameter size via increasing the width m. Sorry, for the red curve, we increase the parameter size via the dimensional width. But for the blue curve, we increase the parameter size via the number of grids. And we can see that for the training, this dashed curve means training loss, they all steadily improves. But the test accuracy, this quantifies the generalization performance. The blue curve increase rapidly, meaning that when we have more grids, the neural network more likely to overfit. Okay, so maybe I will skip these the empirical estimation and these experiments, but just tells you that even in the cases where the theoretical estimation of the optimistic sample size cannot be obtained, there are still ways to estimate the optimistic sample size practically. Okay, for the theoretical estimation of the optimistic sample size estimation, the key tool is the critical embedding, which is obtained from our previous work about the embedding principle of loss landscape. The embedding principle of loss landscape tells you that the loss landscape of neural network contains all the critical points of the narrower or shallower neural networks. So this embedding principle gives you a variety of the critical embedding operators. These operators has the rank preserving properties, and that therefore can be used as an important tool for the optimistic estimate. I will not go into the details, but just tell you that as long as we have the embedding principle, that gives you a family of critical mappings, and the critical mapping will give us an upper bound of the optimistic sample size. So as long as we have the embedding principle in width, and we also prove the embedding principle in depth, this two tells you that we can scale up the width and also the depth freely without worrying about the reduce of sample efficiency. And that is some illustration of these embedding operators. And I will also skip this kind of theoretical results regarding the criticality of optimistic sample size. As you can see, we get a number when you give me a target function and the model. So we can ask whether this optimistic sample size is a critical value in terms of the recovery of target. However, the global recovery theory is very, very difficult because it requires analysis of the nonlinear global training trajectory. However, we can develop some local theory to understand whether it's in some local sense, this optimistic sample size is critical. And here, I just show all the series of works regarding the optimistic estimate and the embedding principle and the condensation. And these two series of work provides very solid foundation for the optimistic estimate. And the embedding principle and the embedding operators serves as a very important tool for the optimistic estimate. And the condensation serves as a strong justification of the relevance of the optimistic estimate. And here's a take-home message. So I just want you to remember the following picture of the sample size requirement for the nonlinear models. So if you develop some nonlinear model and you have a target that the model can fit, and you can easily obtain a pessimistic estimate, just use a number of parameters as a sample size requirement. And also you can use our definition of the optimistic sample size to get a lower bound estimation. And in practice, what you should expect is somewhere in between, meaning that we may need the sample size a little bit greater than the optimistic one for the recovery. So with this picture, and you may ask how we can improve the sample efficiency. And mainly there are two ways. The first is to improve the potential, meaning that if you given the target F star, if you can develop an architecture that has a lower optimistic sample size, that improves the potential. So essentially it is to optimize the architecture. For example, for the from the fully connected neural network to the convolutional neural networks for the CNN, for the image problems. So that kind of improvement is to improve the potential of the sample efficiency. And the second is to unleash the potential, meaning that we can optimize the hyperparameter, for example, the initialization scale, weight decay rate, and learning rate. We're doing that in order to facilitate the condensation. And the more condensed the training dynamic is, the closer the practical sample size is to the optimistic sample size. That is the understanding we previously shows. And these two different methods are the key means to improve the sample efficiency in practice. And for different problems, you can consider different strategies. And so thanks for listening.
Yeah, thanks, Yaoyu, for wonderful talk. And do we have any questions from the audience? Yeah, we got a question in this chat. Yaoyu, can you see it?
Yeah, interesting topic. How do we define the quality of our learning samples? Like we cannot solve questions and solve equations by bad samples. When we had a calculated sample size, how does make us confident to get our models well trained? Okay, so this is a very good question. So first of all, the quality of the samples is a very important issue for the training. And one understanding from the optimistic sample size is that, so this optimistic sample size is a lower bound, meaning that with less samples, you cannot do that. But even though you get enough samples, if these samples are highly correlated with one another, in practice, it is still very difficult to achieve these optimistic performance. So you may need to guarantee that all these samples are not so correlated with one another. Each of these samples provide some independent piece of information, so that this helps better realize the potential of the model. So the second question is about how does make us confident to get our model well trained. So essentially what we do is two things. So when we have some, for example, the estimation of optimistic sample size, the first thing is that we may prepare the samples larger than the optimistic one, because lower one, you will never get any good performance. Larger, for example, twice may be a very safe, twice the optimistic sample size may be safe. And in practice, you can also use the second one, meaning that you can optimize the hyperparameters. If you does not, you just set up all the hyperparameters very carelessly, meaning that you just set them to some arbitrary values. I can guarantee that you may obtain a performance very close to the pessimistic one. However, if you optimize them properly, and then you can expect just use a practical sample size at the similar order of the optimistic one, you can recover the target. So that is the information we can obtain from the estimate.
Yeah, there's another question about unleashing the potential. Are there guidelines for how to adjust the learning rate decay, essentials as the model size scales up?
Okay, so essentially, because we have understanding about condensation, so our now the understanding of the initial scale is that if we scale down the initialization scale, then it condenses more heavily. And we also have some theoretical result. And the weight decay rate, if it's larger, and the learning rate becomes larger. So the information is that the lower initialization scale, larger weight decay rate, and a larger learning rate has a stronger condensation. And this leads to a lower practical sample size. Practical sample size. So that is the basic information about the relation between these hyperparameters and the realization of optimistic sample size. Yeah, so Zhiqing also have some comment.
Yeah, do we have more questions? We also want to thank the audience for proposing these very wonderful questions, and also Yaoyu has given a very wonderful talk. If we don't have more questions, we will stop here, and this talk will be recorded and posted on YouTube. And welcome to this one word machine learning. Again, thanks. Okay?
Thank
you. Okay, goodbye.
Bye.